In this lesson, we're going to look at how we can graph exponential functions. So before we do that, let's talk about what exponentials are. So growing or decaying exponentially means growing or decaying at a really fast rate. So I'm sure that you've heard about this in the real world. Some examples of exponential growth or decay would be populations, where the population of a country could be growing exponentially. Pandemics, like the COVID-19 pandemic, people were contracting the virus at an exponential rate. Compound interest and rate of cooling. That's like a very specific example. If you watch any of those true crime shows, you can find the time of death of a dead body by the rate at which it was cooling, and that is also exponential. So we will look at these examples throughout the course of this unit, but first we're just going to talk about what exponentials are. So basically, an exponential function means that the variable is in the exponent. So here, 2 to the x, we can see that x is our variable, and that is in the top of the function. So let's fill in this table. If x is 0, 2 to the 0 power is 1. Now let's go in the positive direction. So 2 to the first is going to be 2. 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16. And 2 to the fifth is 32. So we can see as the x's are increasing, even just by 1 at a time, the y values are increasing exponentially. When we go in the negative direction, so if we plug in -1 for x, 2 to the -1, if I have a negative exponent and we want it to become positive, we can bring it to the denominator. So 2 to the -1 is the same thing as saying 1 over 2 to the positive 1. And we know that 2 to the first is 2, so 2 to the negative first is 1/2. If I plug in -2, 2 to the -2 would be 1 over 2 to the positive 2, which is 1/4. So 2 to the -3 is 1/8. 2 to the -4 is 1/16, and 2 to the -5 is 1/32. So we can see from here that as x gets more and more negative, the y value again is going to be, in this case, decreasing exponentially. But what we'll notice here is that the y value is never going to reach 0. So when we plug in 0, we get 1, right? Because 2 to, or anything to the 0 power is 1. When I plug in any positive number, my number gets larger. If I plug in any negative number, my number gets smaller and closer to 0. So in my fraction, my denominator is getting larger and larger and larger. So when the denominator is very large, that means that the number is approaching 0. And this is a key fact for exponential functions. So let's look at exponential graphs. So what I have boxed here, this is the basic exponential function. So a times b to the x. So a and b are going to be numbers. And when we do examples that have numbers in them, you'll see that that makes more sense. The only variable we have here is the x, and that, again, notice is in the exponent. We're going to refer to the b value as the base of the exponential. So whatever the number is that's directly attached to the exponent is our b. And that b can have two different scenarios. That b could be greater than 1, or it can be a number between 0 and 1. Those are the only options of what b can be. B can never be negative. The only way to make b negative is if a was negative, then the b is still positive, but it's multiplied to a negative number, so that can happen. But the b itself will always be a number greater than 0. If it's between 0 and 1 as a fraction, that is called an exponential decay. If b is greater than 1, it is called an exponential growth. So a couple things we're going to look at here. In an exponential, we'll start with the exponential growth. We saw in the previous slide that no matter what we plugged in for x, y was never going to reach 0. It was going to get closer and closer and closer to 0, but not reach that. So we're going to draw in this dotted line here. And this is very important. So y equals 0 in this case is where our graph can't touch or cross because it can't ever equal 0. And what this is called is a horizontal asymptote. And we're going to be talking about asymptotes for throughout this course. of this unit as well as other units in the future. There are different types of asymptotes you can have, and in exponential graphs, we only have horizontal asymptotes. Basically, what that means is this is a boundary line. This is saying that your graph cannot touch or cross this line. So it's not really there. It's an imaginary line. It's not actually going to show up on your graph, but when we draw it, we will draw it as a dotted line. Since it's never going to touch or cross the x-axis here, that means that there won't be an x-intercept on this particular graph. Now, if the graph is moved around, and we'll look at that in a little bit, there could be an x-intercept, and that's okay. But typically, if we're looking at the basic like parent function, there is no x-intercept. There is a y-intercept. That's where it crosses the y-axis. So I'm just going to put it here. And the shape of an exponential growth, it goes from low and then goes to high. So low to high from left to right means that the graph is growing. So our graph is going to look something like this. Okay, so this is a typical exponential growth function. A couple of things to note about this. To find the y-intercept, we're going to plug in 0 for x. Now that's the case for any function that exists. If I want to find the y-intercept, we plug x in for 0. Right? If it's crossing the y-axis, x has to be 0. So if I plug this in, a times b to the 0, well, b to the 0 is going to be 1, right? Anything to the 0 power is 1. And I'm multiplying a times 1, so I get a. So my y-intercept would be 0, comma a. If I look at the end behavior, so let's look at the ends here. We talked about end behavior in our other functions as well. Here on the right-hand side, we want to see what is x approaching, what is y approaching. So x is approaching infinity as y approaches infinity. Right? They're both positive. They're up here in this first quadrant. X and y are both positive. On the left end here, x is approaching negative infinity because it's going to the left, but y, instead of approaching either infinity or negative infinity, because it's going straight and it's kind of almost parallel to this asymptote, we're going to say that y is approaching 0. So y will approach the asymptote here. It's not going to go below it, and it's not going to go back up towards infinity. So then let's lastly talk about domain and range. Now the domain for any exponential function will be negative infinity to positive infinity, all real numbers. So we can see that the arrows are going in both directions. X is going from negative infinity to positive infinity. All x's are part of this graph. The range, we're looking at the y's. So for the range, the lowest y that we would have on this graph would be 0. It's not going to ever equal 0 because that's our asymptote. So it's going to be a parenthesis when we write the range. Now, normally when we write the range, we do have a bracket and it includes the number. But because 0 is our asymptote and we can't actually touch it, we're never going to equal 0. So we have parenthesis 0 to infinity. So our lowest y would be something close to 0. That's why it's a parenthesis, not a bracket. And our highest y is going to be positive infinity. So this is the basics of an exponential growth. Now, if we look at an exponential decay, it's going to have a lot of the same properties. So here again, we do have this horizontal asymptote. So y equals 0 again will be our horizontal asymptote. I'm going to shorthand it by writing HA. Again, it will have a y-intercept. There's no x-intercept because of that horizontal asymptote. And an exponential decay function will go from high to low. So it's decaying. So it's going to look something like this. So you can see it's kind of like the mirror image of the exponential growth. Okay, so from left to right, it's going down, so it's decaying. And then the y-intercept, again, will be 0, comma a, because if we plug 0 in for x, we're going to end up with the same thing we have over here. The domain and the range are going to be exactly the same for this one because of, well, the domain is always going to be the same. And then the range, because that horizontal asymptote of y equals 0 is at 0, the lowest we can have is whatever's closest to 0. Highest would be positive infinity. And then let's look at our end behavior. So over here on this left end, x is approaching negative infinity because it's on the left. Y is approaching positive infinity. So it's in the second quadrant. X is negative, y is positive. On the right side, x is approaching positive infinity as the x's are getting larger, and y is going to be approaching 0, again, our horizontal asymptote. So you can see that a lot of these are very similar. So these are the basic graphs of exponentials. Now, if we take these graphs and we perform transformations that we've done before in other units, we will get the same shape but kind of in different locations. So there's really only two types of transformations we're going to focus on. And the first one we're going to look at are translations or shifts. So there's a little note down here, and this is very important. So translations may change the y-intercept, the range, and the horizontal asymptote. So the domain we said was the same for everything. Okay? But if I was to compare these original graphs with their transformations, some things have shifted. So we want to make sure that we understand what's actually moving. So first we're going to look at a translation up. So similar to what we've done with up translations in other functions, if there's something added outside of the function, so there's a plus c outside of this function, that means it's going to move up that amount. Now, normally the horizontal asymptote is at 0. That's where it's always starting. And then we're taking the entire function and we're moving it up c. So when we shift our function up c, the horizontal asymptote is also shifting up that amount. So our horizontal asymptote in this case is y equals c. For the y-intercept, we're going to plug in 0 for x. So that's how we are always finding the y-intercept. So if I plug in 0 for x, we know that b to the 0 is 1, and a times 1 is a. So we end up with a plus c. And then our range, the range will always match the number that is our horizontal asymptote. So we can see here that the lowest y value we have is c, and then the highest is infinity. So the horizontal asymptote of c and the range starts at c, so same value. If we're translating this function down c, okay, so we're subtracting a number from the function, where we're shifting the entire graph down a certain amount, so the horizontal asymptote will also shift down that amount. So the horizontal asymptote in this case, again, would be y equals c. In this case, c is a negative number since it's below the x-axis. The y-intercept, again, we'll plug in 0 for x. So a to the times b to the 0 minus c. B to the 0 is 1 times a. So we get a minus c as our y-intercept. And then our range would be c to infinity, since c is the lowest y value we have. And remember that in this case, c would be a negative number. If we have a shift to the left, that's when we have something that's added inside our function. It's added to the x. So notice that the plus c is attached to the x that's in the exponent. So this means it's going to be a shift to the left. Now, if I'm moving my entire graph to the left, the horizontal asymptote will not change. The only time the horizontal asymptote moves is if the graph is shifting up or down. If it's moving left or right, the horizontal asymptote stays put. So here, the horizontal asymptote is y equals 0. It did not move. The y-intercept, again, we're going to figure it out by plugging in 0. So a to the, not a to the b, excuse me, a times b to the 0 plus c. So now that I'm adding c to 0, instead of having b to 0 like I did in these other cases here, I have b to the c, because 0 plus c is c. So that's going to be a b to the c, and that's going to be some number, right? B to the c is some number. We're multiplying it to a, so a b to the c. And then our range, since our horizontal asymptote was 0, we know that our range will be 0 to infinity. And then lastly here, for a right transformation, we're going to be subtracting c from x in the exponent. And again, it's moving to the right, so our horizontal asymptote will not change. So that will stay at y equals 0. For the y-intercept, we're going to plug in 0 for x. So 0 minus c is negative c. And again, this is going to be some number. And when we do this with actual numbers, this will hopefully make more sense. I know this is a little bit more abstract. And our range will be 0 to infinity. So the last transformation that we're going to look at is a reflection. And just as before, there are two reflections. There's a reflection over the x-axis and a reflection over the y-axis. If we have a reflection over the x-axis, that means that there is a negative in front of the function. So in this example, we have the original function would look like this red graph. Right? That is an exponential growth. If I reflect it over the x-axis, it will look like this blue graph. Okay, so it's pretty straightforward. It's just reflected over. Now the reflection over the y-axis is a little bit tricky. So if it's a negative in the exponent, meaning that the x is a negative value, that is a reflection over the y-axis. Now the original function here was a growth function. It was this red function. If we reflect this over the line, over the y-axis, we end up getting the blue function, which looks like an exponential decay. So when we are reflecting over the y-axis, what our graph is or is supposed to look like will switch to the opposite. And that's what I have in this note down here. So a y-axis reflection makes the function switch from a growth to a decay or vice versa. So let me give you a side example here. So if I have a function y equals 2 times 5 to the negative x, based off of our knowledge of what b is, right? So b is going to be 5. B is what's attached to the exponent. 5 is greater than 1. So since our b value is greater than 1, this would be a growth. But because it's reflected over the y-axis, this negative in the exponent actually makes it a decay. So it was a growth, but because it's reflected over the y-axis, it will become a decay function. So when we draw it, it will be a decay. Same thing goes for the other way around. If I have 2 times 1/5 to the negative x, the 1/5 is my b. It's a number between 0 and 1, so it indicates that it is a decay function. But this negative in the exponent will reflect it over the y-axis, and this actually makes it a growth function. So when we graph it, it will be a growth function. All right, so now let's actually kind of put all these things together that we talked about and see how this stuff works. So when we're graphing exponential functions, we don't actually have to graph them very precisely. Like we're not going to make a table of values or like do anything crazy. The only things we need to have on our graph are the horizontal asymptote and the y-intercept. Once we have those graphed, we're just going to use our knowledge of the shape of the graph to just kind of sketch it and fill it in. So before we decide what this is going to look like on our actual graph, let's look at the equation. So here we have f of x equals 3 to the x plus 6. The 3 here is our base. That's our b. And it's greater than 1. So this means it will be a growth. Okay, then from here we want to look for any transformations that happen. The only transformation we have is this plus 6. And that means it's going to move up 6. So if we have a normal growth function, that means that the horizontal asymptote would be at y equals 0, but now we're shifting it up 6. So our horizontal asymptote is going to be y equals 6. Right? It's going to be y equals that c value, however much it went up. So when we're graphing this, it doesn't have to be very precise. I don't have to make tick marks and like count up 6. I'm just going to do this and say y equals 6. Okay, so here is my horizontal asymptote. To find the y-intercept, I'm going to plug in 0 for x. So if I plug in 0 for x, I'm going to get 3 to the 0 plus 6. So 3 to the 0 is 1. 1 plus 6 is going to give me 7. So I have a y-intercept of 0, 7. So I know that 7 is above 6, so I'm just going to put the dot here. Okay, so now I'm just going to sketch this. It's a growth function. That means it's going to go from low to high. So my graph is going to look something like this. Okay, and from here, we can be able to find our domain, which again is the same for everything. So negative infinity to infinity. Our range, our lowest y value that we have would be the horizontal asymptote. So 6, but it has a parenthesis because it doesn't include 6. Highest y, infinity. If we wanted to fill in our end behavior, I'll just do that for this one here. On the right end, x is approaching positive infinity, y approaches positive infinity on the right. On the left, x approaches negative infinity, and y approaches 6. Okay, so let's look at number 2. So first, let's recognize the base. So 2 is our base. It's greater than 1, so it's a growth. Okay, now let's look at our transformations. So we have a negative in front of the x. So that means that this is going to be a reflection over the y-axis, which means that the graph will actually be a decay function. Because it's reflected over the y, this becomes a decay function. This plus 2 means it's going to the left 2, and this minus 4 means it's going down 4. So when I go to figure out the horizontal asymptote, I only care about where it's moving up or down. So it is moving down 4, so y equals negative 4 is our horizontal asymptote. So I'm going to go over here, and I'm just going to draw a dotted line here, y equals negative 4. For the y-intercept, I'm going to plug in 0 for x. So 2 to the negative 0 plus 2 minus 4. So 0 plus 2 will give me 2, but now it's negative, so negative 2. 2 to the negative 2 is 1/4, minus 4 is going to give us negative 15/4, which is negative 3.75. So that is going to be somewhere right here. Right, it's above negative 4 and below the x-axis. And even though it moved left 2, I don't have to do anything with that in terms of graphing it. Because of the y-intercept that we found, that's indicating that the y-intercept was moved 2 to the left. So we don't have to worry about any other points. And then we said that it was a growth, but because of that reflection, it is a decay. So our graph is going to go from high to low. So it's going to look something like this. Pretend that it goes through that point that I made. Okay, and then domain, again, will be all real numbers, meaning negative infinity to infinity. And our range will be negative 4 to infinity. And I'm not going to fill in the end behavior, but you can figure out what that one is. Okay, so let's look at a couple more. So number 3, first thing we look at is b. So remember, b is what the exponent is attached to. So 1.5 is our b. It's greater than 1, so it's a growth. Then we look for transformations. The negative that we have in front of the x means that this is a reflection over the y-axis, which means that this is actually going to go from a growth to a decay. And there's no movement up or down. There's nothing being added or subtracted. So the horizontal asymptote is y equals 0. And I'll fill that in here. Oops. Okay, and then our y-intercept, plug in 0 for x. So we have 3 times 1.5 to the negative 0. Well, negative 0 is just 0. 1.5 to the 0 is 1. And then we're multiplying it by 3. So 3. So 0, 3 would be somewhere here. Okay, and this was a growth, but because of that reflection over the y-axis, it's a decay. So we're going to go from high to low. Oh, I'm really bad at drawing these. High to low. There we go. And again, domain will be negative infinity to positive infinity, and the range will be 0 to infinity. Okay, and then this last example, we look at the b. So the 1/2, that's between 0 and 1. So this is a decay function. Then we want to look for transformations. So we see a negative in the front. That means that it's a reflection over the x-axis. And that does not change the function. That does not change it to a growth from a decay. It only happens when it's a reflection over the y. So it's a reflection of the x. And then this +1 is moving up 1. So since it's shifted up, our horizontal asymptote will change. So it's y equals 1. For the y-intercept, we're going to plug in 0 for x. So I'll do that over here. -2 to the 1 times 1/2 to the 0 plus 1. So 1/2 to the 0 is 1. 1 times -2 is -2 plus 1 gives us -1. So let me put in, here's my horizontal asymptote, y equals 1. 0, -1 is about here. That's the y-intercept. And because it is a decay function and it's reflected over the x-axis, we want to think about what this is going to look like. If I try to draw a decay function right from here, it's going to kind of cross through that horizontal asymptote, and it can't do that. So the original graph, before we reflect it, would be a decay function that looks something like this. So if I take this graph and I reflect it over the x-axis, I'm going to get a graph that looks something like this. So I'm going to get rid of this piece up here. Okay. So our domain, again, negative infinity to positive infinity, always the same. And our range will be negative infinity to 1, lowest y to highest y. And then let's just do our end behavior real quick. On this left end, x is approaching negative infinity, y is approaching negative infinity. On the right, x is approaching positive infinity, and y is approaching 1, which is our horizontal asymptote.